All right, chemistry, this is your video lecture for Chapter 6, Section 2. In Section 1, we introduced the way that you are to classify the different bond types according to electronegativity difference. We also hit home the idea that nature favors low energy configurations. So when we're trying to explain why a particular set of atoms are bonding, we simply say because it's a lower energy configuration. Now, there are going to be various strategies for accomplishing that lower energy configuration, and that's going to depend on the types of atoms that are in fact bonding. In this section, we are going to deal with covalent bonding, and covalent bonding is going to be experienced between non-metals. When you have a non-metal bonding with a non-metal, there's a specific strategy for achieving your lower energy configuration, that noble gas electron configuration. It involves sharing electrons. Okay, so after this video, you should be able to define molecule and molecular formula. You should be able to explain the relationships between potential energy, distance between approaching atoms, bond length, and bond energy. State the octet rule, which I'm sure you can already do that, so that one's easy. List the 6 basic steps used in writing Lewis structures. Explain how to determine Lewis structures for molecules containing single bonds, multiple bonds, or both. And then explain why scientists use resonance structures to represent some molecules. So here we go. So a molecule is a neutral group of atoms that are held together by covalent bonds, specifically covalent bonds and specifically neutral groups, meaning overall there can be no charge. It has to be neutral, electrically neutral, and everything has to be covalently bonded. And remember, we experience covalent bonding between non-metals. A chemical compound whose simplest units are molecules is called a molecular compound. It is a molecule. It's molecularly bonded, covalently bonded. It's a molecular compound, as opposed to ionically bonded, an ionic compound, or metallically bonded.
Molecule. A molecule is a neutral group of atoms held together by covalent bonds. Water, oxygen, and sucrose, or table sugar, are examples of molecules.
And again, Robot Lady just laid out 3 different molecules for us, examples of molecules, and please note that every single atom that is in each of these 3 molecules, they're all nonmetals. They're all nonmetals. Nonmetals experience covalent bonding with other nonmetals. Therefore, they are considered molecules. The composition of a compound is given by its chemical formula, and you already have experience with chemical formulas. A chemical formula indicates the relative numbers of atoms of each kind in a chemical compound by using atomic symbols and numerical subscripts. A molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. Think of a molecular formula as a chemical formula, because it is a chemical formula, but again, specifically looking at neutral groups of atoms that are covalently bonded together. Here are a couple terms that you need to easily and quickly understand when you hear them: monatomic, diatomic, and polyatomic. Mono referring to one, atomic referring to atom. That's one atom. We can see one atom here of sodium. This is a monatomic atom. Monatomic, just one of them. We have diatomic, di referring to 2. Diatomic, 2 atoms. And so we have a diatomic molecule here. We have fluorine as F2. It takes 2 fluorine atoms to make 1 fluorine molecule. It's a diatomic. But we also have polyatomic molecules. Water, for example, is H2O. We all know that there are 3 atoms in every molecule of water. It's polyatomic. Now remember, bonds form so that atoms can achieve the lowest energy configuration possible, because nature favors low energy configurations. It turns out that most atoms will have lower potential energies when they are bonded to other atoms than they have as independent particles. And so if you have to compare the energy of independent particles and bonded atoms, the bonded atoms are going to have a lower potential energy, and so nature will favor that configuration. This figure below shows the potential energy changes during the formation of a hydrogen-to-hydrogen bond, and we're going to refer to a hydrogen-hydrogen covalent bond several times throughout this video lecture. I want to point out that on the y-axis we have potential energy measured in kilojoules per mole, so it's energy, how much energy is present in the system. And on the x-axis we have the distance between the 2 hydrogen nuclei, right? So as we go to the right on the x-axis, the distance between the 2 hydrogen nuclei is increasing. And what we see is when we have the distance between the 2 nuclei being very, very, very small, or very, very, very large, we see that the potential energy is very, very high. And so nature is not going to support, is not going to favor either of these configurations. However, this configuration, this distance between the two nuclei, results in a situation of the lowest energy possible, lowest potential energy possible. And it just so happens that for two hydrogen nuclei, that distance occurs at 75 picometers, which is a very small distance, but any smaller than that, we're going to be introducing energy into the system, creating a higher potential energy, and nature does not favor that. Nature favors low energy configurations. So here's a graphical representation of that balance between the attractive force that is experienced between protons of one atom and the electrons of another, right? Opposite charges attract, but also like charges repel. So while the electron from one atom is attracting the nucleus of the other atom, at the exact same time, the two nuclei are repelling each other, and the electron clouds of each atom are repelling each other. And so there's attraction and repulsion happening at the same time. These two forces cancel out when a covalent bond is formed at a specific length where the potential energy is at a minimum. In other words, when those two forces, the attraction force and the repulsion force, when those two forces are in perfect balance, the energy, the potential energy of that system is at an absolute minimum, and nature will favor that configuration. So again, here's a representation of that happening. We see it between negatives and negatives, or positives and positives. We see the blue repulsion arrow, and between positives and negatives and positives, we see the red attraction arrow. When both of these forces, right, the net result of these two forces is in balance, a covalent bond is formed. Now, there are a couple of ways that we can describe covalent bonds. One of them is bond length. The distance between two bonded atoms at their minimum potential energy, because that's where they're going to be when they formed a covalent bond, is called the bond length, the distance between the two bonded atoms. In forming a covalent bond, the hydrogen atoms release energy. They release energy. Now, we know that because of the law of conservation of mass and energy. If we're going to take two atoms that are at a relatively high potential energy, bond them so that they move to a lower potential energy state, that energy has to go somewhere. The energy that you lost, going from high energy to low energy, it has to go somewhere. It can't just disappear. And so it's released. Okay, energy is released. In forming a covalent bond, hydrogen atoms, which is the example that we're working with right now, release energy. That exact same amount of energy must be added if we ever want to break those bonded atoms apart again. And sometimes we do, especially in certain industrial processes. That amount of energy that's required to break the chemical bond to form the two neutral isolated atoms is known as bond energy. So don't mistake bond length and bond energy. One is a length, one is amount of energy. So here's that representation of bond length. Sticking with our example of two hydrogen atoms bonded together, they have a bond length of 75 picometers because this distance between the two nuclei is the distance at which the attractive forces and repulsive forces are perfectly balanced out, resulting in a low energy configuration.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
So in this class, we will not be using bond energies to do calculations all that much, but if you decide to try your hand at AP chemistry, we will actually do some thermodynamic calculations using Hess's law, which is surprisingly simple, by the way, and you'll be using these values. But please understand, anytime you do anything with these values, whether it be in general chemistry, honors chemistry, or AP chemistry, you do not have to memorize these values. It's just like the molar masses of the periodic table. You have a periodic table so that you don't have to memorize them. You simply look them up and use that information. Same thing with these bond energies. You're either going to have values printed for you on your quiz, on your test, or you're going to be having access to some sort of appendix in your book. Do not spend any time memorizing these. I want you to focus on learning how to use them. Now, there is a relationship between bond energy and stability. The larger bond energy, meaning the more energy is released, that means that there's a bigger drop in potential energy when that bond is formed, resulting in greater stability. There's also a connection between stability and bond length. A bond is going to form when atoms are at a certain distance from each other, right? At this distance, we know that the atoms are in a low energy state, right? That's why they formed the bond in the first state, or in the first place. If they are closer together than that, or farther apart than that, they will be in an unstable situation. Please understand, you don't have to know how unstable. You do not have to have a number on that. You just need to know that relative to the minimum potential energy state it was in, whatever state it's in now is unstable relative to that state. So we see that bond length also represents a position of stability. When two hydrogen atoms are 75 picometers from each other, that is the most stable situation for hydrogen to be in. And so we're going to see that at these particular bond lengths, right, hydrogen bonded to fluorine, carbon bonded to fluorine, oxygen bonded to oxygen, that there's going to be a very specific bond length that results in the most energy being released, and therefore the most energy being required to be put back in to break that bond, known as bond energy. When two atoms form a covalent bond, they share their shared electrons, right? The electrons that are going into that bond form overlapping orbitals. And in order to picture that, let's go back to something that we covered in Chapter 4, orbital notation. We know that hydrogen has one electron and it's one s orbital. And so if we're going to form a hydrogen molecule out of two hydrogen atoms, which is the example that we are working with, in order to satisfy Hund's rule, we're going to have to fill the other orbital with an electron of opposite spin, right? Also to satisfy the Pauli exclusion principle. But you'll notice that we already have one of the electrons in the hydrogen's 1s orbital spin down. You might be curious, how am I supposed to know that I'm supposed to write it with down spin? And in one sense, you don't. Please remember that these atoms exist in three-dimensional space, and they can rotate and they can move around in three-dimensional space. And so as long as these two hydrogen atoms are rotated relative to one another from each of their perspective, it's going to seem like the electron of the other hydrogen is in fact of opposite spin. And as long as those orbitals overlap in three-dimensional space, those electrons are going to inhabit both orbitals at the same time. The 1s orbital from the first hydrogen and the 1s orbital from the second hydrogen. This will achieve a noble gas configuration, aka the lowest energy configuration possible. The bonding of these two hydrogen atoms allows each atom to have a stable electron configuration, that of helium, which is a noble gas, but doesn't have an octet, it has a duet. Let's quickly remind ourselves of the Octet Rule. Noble gas atoms are unreactive because of their electron configurations are especially stable. This stability results from the fact that the noble gas atoms' outer s and p orbitals are completely filled by a total of 8 electrons. Other atoms can fill their outermost s and p orbitals by sharing electrons through covalent bonding. That's what we're doing in this section. We're talking about covalent bonding, and covalent bonding is a strategy to satisfy the Octet Rule, gain a noble gas electron configuration, and achieve the lowest energy configuration possible. Sharing electrons is simply one of those strategies. Chemical compounds, any chemical compounds, not just molecules, but also ionic compounds and metals, samples of metals and alloys. Chemical compounds tend to form so that each atom, whether by gaining, losing, or sharing electrons, has an octet of electrons in its highest energy level. Now, right now, please understand, we're not talking about gaining or losing. That's going to be more specific to ionic bonding and even metallic bonding. Right now, in Section 2, we're talking about covalent bonding, so we're focusing on the sharing more.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons, 8 in most cases and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of two atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
Now, there are some exceptions to the octet rule that we want to be aware of. Right? Exceptions to the octet rule include those atoms that cannot fit 8, meaning they can only do less than 8, fewer than 8, and for those that can fit more than 8 into their outermost orbital. And so examples of elements that cannot fit all the way up to 8, we have hydrogen. Hydrogen forms bonds in which it is surrounded by only 2 electrons. So it's not an octet, it's a duet, right? But hydrogen and helium are the only exceptions in that same way. Boron has just 3 valence electrons, so it tends to form bonds in which it is surrounded by 6 electrons, right? So it's bringing 3 to the table. That means that it can form 3 bonds, right? 3 bonds is 6 electrons. But then main group elements in periods 3 and up can form bonds with expanded valences, right? That means involving more than 8. We're not going to deal a lot with those in this course because that involves some extra electrons being used from the D sublevel, and that's just a little bit beyond the scope of this course. We want to stick more often than not with the rule itself rather than the exceptions. Now, one thing that's going to really help us predict bonding, and then in section 5, predict molecular geometry, is by using something called Electron Dot Notation. To keep track of valence electrons, remember the ones that are responsible for bonding, this is chapter 6, bonding, it is helpful to use Electron Dot Notation. Electron Dot Notation is an electron configuration notation in which only the valence electrons of an atom, of a particular atom, are shown, or element are shown. They are indicated by dots placed around that element's symbol. The inner shell electrons are not shown. And please understand, we're not saying that the inner shell electrons are unimportant. In fact, they're very important. If you remember from last chapter, we excruciatingly tried to demonstrate that the inner shell electrons are responsible for electron shielding and the changes that are observed in effective nuclear charge, which leads to the various periodic properties of the elements. And so inner shell electrons are important. However, we're talking about that in chapter 5, talking about periodic properties. Here in chapter 6, we're talking about bonding. And so since only, for the most part, the only electrons that are involved in bonding are the valence electrons, in this chapter, we only need concern ourselves with valence electrons. And so using the last slide as an example, I would like you to press pause on the video and create a response to each of these 2 sample problems. Write an electron dot notation for hydrogen and nitrogen. Please press pause now. So hydrogen, we know, is in group 1 and only has 1 valence electron. We also know that its symbol is H, so we draw an H with 1 electron around it, represented by a dot. Nitrogen, however, is in group 15. It has 5 valence electrons. So around its symbol of N, we have to place 5 valence electrons. Just as a subtlety right here, please note that only 2 of these electrons are doubled up. 3 of the electrons are by themselves. They're unpaired. This is reminiscent of the orbital diagram of nitrogen. Remember, we have an s orbital and then 3 p orbitals. For nitrogen, having 5 valence electrons, the s orbital is going to be doubly filled, while each of the p orbitals will only have 1 electron in each of them. And we are actually representing that by spreading out these valence electrons around nitrogen in this way. Electron dot notation can also be used to represent molecules. When we're representing molecules using electron dot notation, they're referred to as Lewis structures. And so I would take 2 hydrogen atoms, place them right next to each other, and place each of their lone electrons in between the 2 symbols. The pair of dots now between the 2 symbols represents the shared electron pair of the hydrogen-hydrogen covalent bond. That is the bond right there. For a molecule of fluorine, however, having several lone pairs of electrons, the electron dot notation for fluorine atoms are combined, and we still see that there is 1 bonding pair and then the leftover valence electrons for each fluorine atom. Continue with this example of fluorine. The pair of dots between the two symbols represents the shared pair for the covalent bond. The two dots in the middle, here highlighted in yellow, are the covalent bond. But in addition to those electrons, each fluorine atom is surrounded by 3 pairs of electrons that are not shared in bonds. Right here they're represented as yellow. An unshared pair, also known as a lone pair, in class I use the term lone pair a lot more, is a pair of electrons that is not involved in bonding and that belongs exclusively to one atom. This pair of electrons right here belongs only to this fluorine, not to its partner. These 2 electrons are not part of the bond. The pair of dots representing a shared pair of electrons in a covalent bond is often replaced by a long dash, and this is what I want us to move towards. So we have that hydrogen molecule with 2 hydrogen atoms. We represent the bonding pair of electrons with a long dash. We also have the fluorine molecule with its pair of electrons forming a covalent bond represented by a long dash. But notice in this structure, I'm still representing each of the valence electrons. Whereas a structural formula, which is a little bit more popular in organic chemistry, also indicates the kind, number, and arrangement in bonds. Right? We still know how many of each type of atom are there and what type of bonds are being formed, but the unshared pairs the unpaired electrons. Sorry, keep on mixing words. The unshared pairs, the lone pairs of electrons on each of the atoms, are not represented. Lewis structures and structural formulas for many molecules can be drawn if one knows the composition of the molecule and which atoms are bonded to each other. A single covalent bond, also known as a single bond, is a covalent bond in which one pair of electrons is shared between 2 atoms. Again, that's one pair of electrons. That's 2 total electrons, 1 pair. When you have 1 pair, it's a single bond. So I'd like you to press pause and attempt this sample problem. Draw the Lewis structure for iodomethane. That's CH3I. Please press pause now. So the first thing we're going to do is we're going to determine the type and number of atoms in the molecule. The formula, the chemical formula, the molecular formula is going to tell us, or it already has told us, that there's 1 carbon atom, 1 iodine atom, and 3 hydrogen atoms. Next, we write the electron dot notation for each type of atom in the molecule. We know that carbon has 4 valence electrons, we know that iodine has 7 valence electrons, and we know that hydrogen has 1 valence electron. And so we draw the electron dot notation for each type of element as such. Next, we determine the total number of valence electrons available in the atoms to be combined, meaning how many valence electrons should be represented in the entire molecule. We know that carbon is bringing 4, iodine is bringing 7, and the 3 hydrogens are bringing 3 for a total of 14 electrons. Now that we know that we should be dealing with 14 electrons, we have to actually create the skeleton structure. If carbon is present, and in this example, in this sample, it is, if carbon is present, it is the central atom. It is the central atom. If carbon is not present, which it won't be sometimes, the least electronegative atom in the molecule is central. You put it in the middle. Unless it's hydrogen, hydrogen is never central. No matter what, it's never central. So we do have carbon, so we put it in the middle, and then we surround that central atom with our 4 remaining elements, 3 hydrogens and 1 iodine. We also place the bonding pair of electrons in between each of those elements to represent the actual bond. Next, we add unshared pairs of electrons to each nonmetal atom, as long as it's not hydrogen, such that each element is surrounded by 8 electrons. Now, the reason we don't do this for hydrogen is because hydrogen doesn't want to be surrounded by 8 electrons. It wants to be surrounded by 2 electrons, right? That duet. But carbon and iodine do want to be surrounded by 8 electrons. We can also have more than one bond, however. A double bond is a covalent bond in which 2 pairs of electrons are shared between 2 atoms, right? 2 pairs, that's 4 total electrons. Double bonds are often found in molecules containing carbon, nitrogen, and oxygen. A double bond is shown either by 2 side-by-side pairs of dots or by two parallel dashes, right? The two strategies that we've already mentioned, we're just putting them side by side to represent that double bond. A triple bond is a covalent bond in which 3 pairs of electrons are being shared between two atoms. 3 pairs, 6 total electrons, 3 pairs. We're going to see this in diatomic nitrogen, for example. This is N2, the type of nitrogen that occurs in our atmosphere, that accounts for 70 to 75% of every breath that you take. We're going to represent that as N with 3 dashes N. Or ethine, C2H2, which is going to have a carbon-carbon triple bond. But remember, we need to satisfy the carbon's octet, and so we have 2, 4, 6 electrons in the middle, and then our 7th and 8th electrons on the outside.
Single covalent bonds are formed when one pair of electrons is shared between two atoms, as shown in this molecule made up of 2 atoms of fluorine. The dots represent electrons. The shared electrons can be represented with a line. This is often simplified to a single dash, representing a single bond between the symbols for the elements involved. Double covalent bonds are formed when 2 pairs of electrons are shared between 2 atoms. Again, each set of shared electrons can be represented with a line. Double covalent bonds are usually shorter and have higher bond energies than single bonds. Triple covalent bonds are formed when 3 pairs of electrons are shared between 2 atoms. Each set of shared electrons can be represented with a line. Triple bonds are usually shorter and have higher bond energies than single or double bonds.
Double and triple bonds are referred to as multiple bonds because there are multiple bonds. In general, double bonds have greater bond energies, meaning they're stronger, and are shorter than single bonds. Triple bonds are even stronger, meaning they have even higher bond energies, and even shorter than double bonds, which makes sense, right? You're providing more attractive force. You're actually holding those two things, those two atoms, together more tightly. When writing Lewis structures for molecules that contain carbon, nitrogen, and oxygen, remember that multiple bonds between pairs of these atoms are certainly possible. So now we're going to get into the steps that you want to follow in order to nail your Lewis structures every single time when you're trying to draw a compound. Now, as you start to move into working on the practice problems on your worksheets, please have these 2 slides out and refer to them actively as you work through these samples. Step 1, gather information. And so what that's going to look like is draw the Lewis structure for each atom in the compound individually, the electron dot notation of that element by itself. And when placing the valence electrons around an atom, place 1 electron on each side before pairing any electrons. Remember, we want to satisfy Hund's rule and the Pauli exclusion principle, and we do that by simply spreading out the electrons before we pair them up. Then determine the total number of valence electrons in that compound. And that last part, determining the total number of valence electrons in the compound, is going to be absolutely critical for you being able to double check your work at the end of the problem. Then, arrange the atoms. Arrange the Lewis structure to show how many atoms bond in the molecule. Now remember, halogens and hydrogen atoms often bind to only one other atom, meaning they only form one bond. And that means that they're usually at the end of a molecule, on the outside. Carbon is often placed in the center of a molecule. And you will find that, with the exception of the carbon, the atom with the lowest electronegativity is often the central atom. Step 3, distribute your dots, your electrons. Distribute the electron dots so that each atom, except for hydrogen, beryllium, and boron, satisfies the octet rule. They want to have 8 valence electrons. Next, draw the bonds. Erase each pair of dots that represents a shared pair, and then draw in a long dash, right? Draw in that bond. Lastly, verify the structure. Double check. Count the number of electrons surrounding each atom. Except for hydrogen, beryllium, and boron, all atoms must satisfy the octet rule. Check that the number of valence electrons is the same number you determined in step 1. So let's go through a simple problem right here. Please press pause and attempt to construct CH2O, also known as formaldehyde. Please press pause now. First, determine the number of atoms in each element present in the molecule. This formula shows that there's 1 carbon, 2 hydrogens, 1 oxygen. Next, we're going to write the electron dot notation for each type of atom. Well, carbon has 4 valence electrons, oxygen has 2 valence electrons, oxygen has 6 valence electrons, and hydrogen has 1 valence electron, and so we'll draw the electron dot notation for each of those as such. Next step, determine the total number of valence electrons available in the atoms that we're combining. We get 4 from the carbon, 6 from the oxygen, and 2 from the 2 hydrogens for a total of 12 electrons. So we need to remember that 12 electrons. Next up, we're going to arrange the atoms to form a skeleton structure for the molecule, and then connect the atoms by electron pair bonds. We have carbon present in this molecule, so it's going to be central. Now we're simply going to spread out the rest of the atoms, which is 2 hydrogens and 1 oxygen, around the carbon. And so we represented each atom as being bonded to each other. Next, add unshared pairs of electrons to each non-metal atom, with the exception of hydrogen, such that each is surrounded by 8 valence electrons. We accept hydrogen here because it only needs 2, only has a duet. All the other nonmetals are going to have 8, so the carbon and the oxygen want to have 8. Now, looking at that structure at the bottom here, we count the number of valence electrons in that Lewis structure to be sure that the number of valence electrons used equals the number available, right? The number that we established in step 1. But this structure, as we've drawn it, has 14 electrons. That means that this structure has 2 valence electrons too many. So how do we fix this? We subtract 1 or more lone pairs until the total number of valence electrons is correct. And we can't just make those valence electrons disappear. What we're going to do is we're going to take those lone pairs of electrons and move them and create bonding pairs, right? We're going to take those lone pairs, turn them into bonding pairs. So we're not making those electrons disappear. We're just having them form bonds. And so when we go to subtract the lone pair of electrons from the carbon, we're also going to move a lone pair of electrons from the oxygen to bond between carbon and oxygen and form a double bond. And so now as we take this lone pair and move it into this space in between carbon and oxygen to form this double bond, as we go back and count the total number of electrons we have 2, 4, 6, 8, 10, 12 electrons. That's the number we were supposed to have. But also notice around each element, with the exception of hydrogen, they just have the 2. There's 1, 2. There's 1, 2. They're happy. But for carbon, there's 2, 4, 6, 8 electrons around carbon. And for oxygen, there's 2, 4, 6, 8 electrons around oxygen. So that is a low energy configuration. That is the lowest energy configuration possible and favored by nature.
Some molecules and ions cannot be adequately represented by a single Lewis structure. At one time, it was theorized that the bonds in molecules like ozone resonated or alternated between single and double bond states. Later investigation proved that the 2 bonds were actually identical. The resonating bonds never existed as pure double or single bonds, but as something in between, both with respect to bond length and strength. The electrons in these bonds were somehow shared evenly across the structure. Electrons shared in this way are said to be delocalized. Resonance is frequently represented by 2 Lewis structures joined by a double-headed arrow.